Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A profound chasm runs through the heart of 19th century physics. On one side stands the magnificent edifice of classical mechanics, a world of particles and planets governed by the elegant, time-symmetric laws of Newton and Hamilton. Within this framework, every interaction is perfectly reversible. A film of planetary orbits or colliding billiard balls run backward is as physically plausible as one run forward. On the other side stands the pragmatic, powerful, and deeply unsettling second law of thermodynamics. Here, time possesses a fierce and undeniable direction. Heat flows from hot to cold, cream mixes into coffee, and systems inexorably evolve toward a state of greater disorder, a greater entropy. The universe, it seems ages, the central intellectual puzzle of the era, a challenge that struck at the very conception of physical reality, was how to reconcile these two pictures. How does the time-reversible dance of microscopic constituents give rise to the irreversible arrow of time we observe at the macroscopic scale? It was into this conceptual crucible that Bennett William stepped, armed with a formidable command of Hamiltonian mechanics and an almost philosophical insistence on logical consistency. He perceived the statistical work of his contemporaries as brilliant yet incomplete, a structure built upon foundations that seemed to assume the very conclusion they sought to prove. His life's work became a quest to bridge this chasm, to derive the laws of heat and entropy from the first principles of mechanics. He aimed to construct thermodynamics from the atom up, to show how the collective behavior of countless reversible particles could forge the irreversible destiny of the world. His initial efforts, focused on the most austere and idealized of scenarios, would lay a new and rigorous foundation for the entire field of statistical mechanics. The core of the problem resided in the nature of entropy and its connection to mechanics. Boltzmann had made monumental strides, proposing that entropy was a measure of the number of microscopic arrangements, or microstates, corresponding to a given macroscopic state. His famous H theorem attempted to show how molecular collisions would, on average, drive a system toward the state with the most possible arrangements, thereby increasing its entropy. This was a revolutionary insight, linking a thermodynamic quantity to statistical probability. Yet, for a mind like Bennett's, a troubling circularity lay buried within the argument. The derivation depended critically on an assumption known by its German name, the *Stoss-Alansatz*, or the molecular chaos assumption. This postulate stated that the velocities of two colliding particles are uncorrelated before they interact. While this seems intuitive, it subtly introduces an element of irreversibility from the outset, a one-way street of forgetting past correlations. To Bennett, this felt like a physicist's sleight of hand, a necessary but unsatisfying leap of faith. He deeply respected Boltzmann's vision, but he sought a more primitive and unassailable starting point, an axiom rooted purely in the mechanics of the system itself. His chosen arena for this inquiry was the conceptual space developed by William Rowan Hamilton. Hamiltonian mechanics describes the state of any system, however complex, as a single point in a high-dimensional abstract space known as phase space. Each dimension of this space corresponds to either a position or a momentum of one of the system's constituent particles. The entire history of a system, its complete evolution through time, is represented by a single, continuous trajectory of this point through phase space. This elegant geometric picture provided Bennett with the language he needed. The problem of thermodynamics could be reframed: how does the motion of a single point in phase space, governed by time-reversible equations, explain the emergence of entropy? Bennett's answer appeared in his 195 paper on the statistical basis of the second law, a work of austere beauty and formidable logic. He began by considering the simplest possible thermodynamic object a perfectly isolated system. This is a system with a fixed total energy, which we can call E, a fixed volume, and a fixed number of particles. In the language of phase space, the conservation of energy means the system's representative point is confined to a specific surface defined by the equation H of P, Q equals E, where H is the Hamiltonian function of all the positions, Q and momentum, P. Bennett drew upon a key result from mechanics, Liouville's theorem, which demonstrates that a volume of points in phase space flows like an incompressible fluid. It can stretch and distort, but its total volume remains constant as the system evolves. This mechanical invariance provided the bedrock for his great postulate. He reasoned that if a system is isolated and has been left to evolve for a sufficient time to reach equilibrium, it has no memory of its specific starting point, only that its energy is constant. With no other information available, there is no mechanical reason to prefer one accessible microscopic configuration over any other. This led him to formulate what he called the phase space density postulate, the cornerstone of what we now call the microcanonical ensemble. The postulate states that for an isolated system in equilibrium, all accessible microstates lying within an infinitesimally thin shell of energy between E and E plus delta E are equally probable. This single, powerful assumption replaced the contested molecular chaos hypothesis. It derived its force from a principle of indifference, grounded in the fundamental symmetries of Hamiltonian mechanics. From this postulate, the entire thermodynamic framework for an isolated system could be constructed. The fundamental quantity became a measure of E, the total volume of phase space occupied by the energy shell. This value, a measure, represents the total number of ways the system can be arranged while respecting the conservation of energy. It is a direct, mechanical measure of the system's microscopic multiplicity. In his 195 paper, Bennett demonstrated this by calculating a measure of E for a monatomic ideal gas. He then proposed a seminal equation connecting the microscopic world to the macroscopic. S equals K log omega of E. Here, S is the thermodynamic entropy. This equation was a thing of profound beauty, directly linking the measurable, macroscopic property of entropy to a purely microscopic, statistical combo states. It is worth noting that in Bennett's original formulation, the constant K was a system-dependent proportionality factor. The realization that it was a universal constant of nature, what we now call Boltzmann's constant, would come later. This detail underscores the pioneering, developmental character of his work. He had forged a critical link in the chain of reasoning, a link that was more rigorous, if initially less general, than Boltzmann's own formulation. conclusion. The immediate impact of Bennett's paper was muted. The world of physics was turbulent, with attention turning toward electromagnetism and the emerging crises that would lead to relativity and quantum theory. His work, with its focus on classical foundations, was seen by some as a meticulous but perhaps backward-looking exercise. Its true significance, however, was recognized by those who shared his passion for conceptual clarity. The paper's moment of revival came in 1911 with the publication of the celebrated review article, The Conceptual Foundations of the Statistical Approach in Mechanics, by the physicists Paul and Tadtwarner Ehrenfest. In their exhaustive survey, the Ehrenfests singled out Bennett's 1895 paper for its exceptional lucidity. They praised his clean, correct articulation of the equal a priori probability postulate as the proper starting point for statistical mechanics. They saw it as the clearest path toward understanding the notoriously difficult ergodite hypothesis, the idea that a system's trajectory will, over time, pass arbitrarily close to every possible state on its energy surface. The Ehrenfest's endorsement served as a powerful conduit, transmitting Bennett's ideas to a new generation of theoretical physicists. Among the most receptive was Richard C. Tolman, who was then embarking on his own quest to systematize the field. Tolman's authoritative 1938 monograph, The Principles of Statistical Mechanics, would become the definitive text for decades, and in it, the influence of Bennett's approach is unmistakable. Tolman adopted the ensemble method, with a microcanonical ensemble for isolated systems as the fundamental starting point, a direct intellectual inheritance from Bennett's postulate. To this lineage, Bennett Williams' rigorous formulation, once an obscure contribution, became an indispensable pillar of modern physics. His work on the isolated system was a triumph of theoretical physics, demonstrating that a universe of irreversible phenomena could indeed be understood as a collective statistical consequence of perfectly reversible laws. Yet, this very success highlighted the next great challenge. After all, few systems in the real world are truly isolated. Most are in contact with their surroundings, exchanging energy, and settling into thermal equilibrium. The next step in his intellectual journey would be to leave the austere perfection of the isolated system and venture into the messier, more realistic world of systems in thermal contact, a step that would require an even more ingenious statistical framework. The triumph of the microcanonical ensemble for isolated systems, a testament to a universe of irreversible phenomena emerging from reversible laws, simultaneously illuminated its own profound limitations. Physics rarely unfolds in a perfectly sealed box. The real world is a complex tapestry of interaction, a domain of systems held in the gentle, persistent grip of their surroundings, exchanging energy, and finding equilibrium. To understand this world, a new statistical framework was essential, one capable of describing the behavior of a system bathed in the constant temperature of an environment. This next phase of Bennett Williams' intellectual journey required him to step away from the austere perfection of the isolated system and confront the rich, dynamic reality of thermal contact. The challenge was immense. The microcanonical postulate, with its strict requirement of a fixed total energy, proved mathematically cumbersome and physically restrictive for most experimental contexts. Calculating the volume of a thin energy shell in a high-dimensional phase space was a task of immense technical difficulty. Moreover, the very premise of perfect isolation was an idealization seldom achieved. A chemist's beaker, a biologist's cell, a planet warmed by its star, these are all open systems. They are held at a roughly constant temperature by a vast reservoir of energy, their own energy fluctuating as they exchange heat with their surroundings. The crucial question became how to construct a probabilistic description for a system whose energy was itself a variable. Bennett's answer, detailed in his 1902 monograph, Statistical Thermodynamics of Coupled Systems, was a work of profound physical intuition. He conceived of a brilliant conceptual maneuver. He considered a small system of interest, which we might call S, in thermal contact with a massive heat reservoir, R. The combination of the system and the reservoir, S plus R, could be treated as a single, enormous, isolated system with a fixed total energy. This allowed him to apply the full power of the microcanonical principle he had already mastered, but in a far more subtle context. The probability of finding the small system S in a specific microstate, labeled I, with an energy E sub I, would be proportional to the number of available microstates for the reservoir, omega sub R. The reservoir, in this scenario, would possess the remaining energy, E total minus E sub I. Here, Bennett's physical reasoning came to the fore. He invoked the fundamental relationship between entropy and the number of microstates. S equals K times the natural logarithm of omega. This means the number of states, omega, is equivalent to e to the power of the entropy S divided by Boltzmann's constant K. Therefore, the probability for the system's state I is proportional to e to the power of the reservoir's entropy, S sub R, divided by K. The decisive step was recognizing that the system's energy, E sub I, is minuscule compared to the total energy of the combined system. This permitted the Taylor series expansion of the reservoir's entropy, S sub R, as a function of its energy. The first term of the expansion is a constant, which can be absorbed into the proportionality. The second, and most important, term involves the first derivative of the reservoir's entropy with respect to its energy. From the laws of classical thermodynamics, this derivative is precisely the definition of the reciprocal of the temperature, 1 over T. Higher order terms in the expansion become negligible due to the immense size of the reservoir. The result was an expression of stunning simplicity and power. The probability of the system being in state I is proportional to e to the power of the quantity negative E sub I divided by the product of Boltzmann's constant and the temperature, KT. This is the celebrated canonical distribution, which Bennett originally termed the isothermal distribution. Its derivation, routed in the physical picture of a system coupled to a BEF, stood in illuminating dialogue with the concurrent work of the American physicist J. Willard Gibbs. In his own 1902 masterpiece, Elementary Principles in Statistical Mechanics, Gibbs arrived at the same distribution to a more abstract, formal pathway, imagining a vast mental collection of similar systems. In his preface, Bennett respectfully acknowledged Gibbs's elegant abstraction, while characterizing his own approach as a physical derivation, one that followed the causal chain of energy exchange. Central to Bennett's formulation was the normalization constant required to turn the proportionality into a true probability distribution. The sum over all possible states, the summation of e to the power of negative E sub I over KT for all I, he termed the Zustan sum, or sum over states. Today, this quantity, universally known as the partition function and denoted by Z, is the cornerstone of equilibrium statistical mechanics, is a veritable Rosetta Stone, a single mathematical object that connects the microscopic world of quantum states and energy levels to the macroscopic world of thermodynamics. From the partition function and its derivatives, one can calculate a system's internal energy, its heat capacity, its pressure, and its free energy, providing a complete thermodynamic description from first principles. To demonstrate the utility of this new framework, Bennett applied it to a pressing problem of the era of the specific heat of solids. Modeling a simple crystalline solid as a collection of classical atoms vibrating about their lattice positions like harmonic oscillators, he used the machinery of the canonical ensemble to calculate its heat capacity. His derivation beautifully reproduced the well-known empirical D'Alembert law, which correctly predicted that at high temperatures, the molar specific heat of many solids approaches a constant value of 3 times the universal gas constant. This result emerged naturally from his formalism as a consequence of the classical equipartition of energy. His analysis, however, revealed something far more profound. The classical model he employed predicted that this value for the specific heat should hold at all temperatures. This theoretical rigidity stood in stark contradiction to emerging experimental data, which showed that the specific heats of solids invariably decreased at low temperatures, approaching zero as the temperature neared absolute zero. In a chapter of his monograph, Bennett explored this failure with remarkable clarity. He identified what he called the caloric freeze-out, the apparent vanishing of thermal degrees of freedom at low temperatures, as a fundamental inadequacy of classical physics. His statistical framework was powerful enough to pinpoint the exact location of the breakdown. It posed a sharp, unavoidable question that classical mechanics was unable to answer. The impact of this work was deep and direct. A decade later, a physicist, Peter Debye, in his landmark 1912 paper that successfully explained the low-temperature behavior of specific heat, gave explicit credit to Bennett's 1902 monograph. Debye noted that it was Bennett's precise and unflinching analysis of the classical model's failure that provided a crucial motivation for seeking an entirely new approach. Bennett had framed the problem perfectly. Debye, armed with the nascent quantum theory of Max Planck, provided the solution by postulating that the vibrational energies of the solid were themselves quantized, existing only in discrete packets called phonons. With the development of the canonical ensemble, Bennett had equipped physics with a robust and versatile tool, one that made the powerful methods of statistical mechanics applicable to nearly any system in thermal equilibrium. He had built a sturdy bridge between the microscopic quantum realm and the macroscopic world of laboratory measurement. This achievement also, by exposing the sharp edges where classical theory crumbled, helped to illuminate the path forward into the strange new landscape of quantum mechanics. The very success of this physical theory raised a deeper philosophical question about its own foundations. If statistical reasoning could so powerfully predict physical behavior, perhaps its essence lay in the very structure of logic and inference itself. This inquiry would lead him toward his next great conceptual synthesis, the reimagining of entropy as a universal measure of information. The stunning predictive power of the canonical ensemble, a tool Bennett himself had polished to a fine sheen, carried with it a profound intellectual disquiet. Its success was undeniable, yet its philosophical underpinnings remained a source of deep debate throughout the 1920s. The probabilities it employed seemed to occupy a strange space between objective frequencies and subjective degrees of belief. If one could derive the macroscopic laws of thermodynamics from statistical assumptions about microscopic states, what was the ultimate nature of these statistics? Were they a reflection of an inherent randomness in the world, or were they a reflection of the observer's incomplete knowledge? This question resonated with a broader movement in logic and philosophy, particularly the work of John Maynard Keynes, whose 1921 treatise on probability argued for a conception of probability as a degree of rational belief, a logical relation between a proposition and a body of evidence. For Bennett, this was a revelation. It suggested that the foundations of statistical mechanics might be placed on a footing as secure and universal as formal logic itself. This line of inquiry culminated in a series of lectures Bennett delivered throughout the late 1920s, a body of work so far ahead of its time that its full impact would only be felt decades after his death. Within these lectures, he articulated what he termed the principle of maximum ignorance. The principle was an audacious attempt to provide a single, unifying rule for assigning probabilities in any scientific context. It proposed that when faced with incomplete information, a set of macroscopic constraints like average temperature or pressure, the most objective and least biased probability distribution one can assign to the underlying microscopic states, is the one that is maximally non-committal about the missing details. The mathematical embodiment of this non-committal or ignorant state was a maximization of the informational entropy, a quantity he defined, following Boltzmann's statistical insights, as H equals the negative summation over all states I of P sub I times the logarithm of P sub I. To maximize this function is to choose a probability distribution that is as spread out as possible, a distribution that contains the minimum amount of information consistent with the known facts. The true genius of this principle was revealed when Bennett applied it to rederive the foundational results of statistical mechanics, stripping them of their conventional physical baggage. Consider his treatment of the canonical ensemble. The standard derivation invoked the physical concept of a small system in contact with a large heat reservoir, with energy flowing back and forth until thermal equilibrium is reached. Bennett demonstrated that the reservoir was a useful physical intuition, yet a logical superfluity. He began with a more abstract problem. Imagine a system that can exist in a set of microstates, each with a corresponding energy, E sub I. The only piece of information we possess from a macroscopic measurement is the system's average energy, which we can write as the constraint that the summation of P sub I times E sub I must equal the observed average energy. With this single constraint, he asked what is the most honest probability, P sub I, that we can assign to each microstate. According to his principle of maximum ignorance, it must be the distribution that maximizes the informational entropy H, subject to the known average energy. This is a standard problem in variational calculus, one readily solved using the method of Lagrange multipliers. The calculation is elegant and stunningly direct. The resulting probability distribution, the one that is maximally ignorant of all other details, takes the precise form of the probability P sub I is proportional to e to the power of negative b times E sub I. This is the Boltzmann distribution, the mathematical heart of the canonical ensemble. It emerged from his analysis without any mention of heat baths, colliding particles, or ergodic hypotheses. The distribution appeared as the unique consequence of applying the rules of logical inference to a state of incomplete knowledge. The parameter beta, which in the physical derivation corresponds to inverse temperature, here arises as a Lagrange multiplier whose value is determined by the average energy constraint. This reconceptualization was a paradigm shift of the first order. It suggested that statistical mechanics was a far more general discipline than physics alone. It was the universal methodology for reasoning in the face of uncertainty. The laws of thermodynamics, in this view, were magnificent applications of this general inferential framework. The second law, the inexorable increase of entropy, became a statement about the evolution of information. As a system evolves, our certainty about its precise microstate tends to decrease, and the distribution representing our knowledge broadens, thus increasing its informational entropy. This provided a compelling answer to the old paradoxes about entropy being a subjective quantity. It is subjective, Bennett's work implied, in the same way that all logical inference is. It depends on the information one possesses. For an omniscient observer who knew the exact position and momentum of every particle, the entropy would be zero. For us mortals, armed only with thermometers and pressure gauges, the entropy is positive and its maximization provides the best possible predictions. This profound reframing of an entire field of physics went largely unnoticed during Bennett's lifetime, confined as it was to his lecture notes and correspondence. The intellectual seeds he planted, however, were destined for fertile ground. Decades later, these posthumously published lectures fell into the hands of the physicist Edwin T. Jaynes. For Jaynes, reading Bennett's work was a moment of profound clarity. He saw immediately that Bennett's principle of maximum ignorance provided the missing logical foundation he had been seeking for statistical mechanics. In his two seminal 1957 papers, which are now considered the founding documents of the modern school of maximum entropy statistical mechanics, Jaynes explicitly and repeatedly credited Bennett as his direct intellectual forerunner. He stated with scholarly humility that his own work was an effort to carry Bennett's program to its logical conclusion. Jaynes formalized the principle, rechristened it the principle of maximum entropy, or max-ent, and demonstrated its enormous applicability. Today, Bennett's inferential viewpoint is the cornerstone of a vast range of disciplines. The max-ent principle is a fundamental tool in modern data analysis. In signal processing, it is used to reconstruct clear images from noisy or incomplete data. In econometrics, it helps build models of market behavior based on limited financial information. In machine learning, the widely used logistic regression algorithm for classification can be derived directly as max-ent model. Each of these applications is a distant echo of Bennett's core insight that the exponential distribution of the canonical ensemble is a beautiful and powerful physical law because it is, at its heart, an unimpeachable statement of logical inference. He had shown that the bridge between the microscopic and macroscopic worlds was built with the planks of probability and held together by the logical mortar of entropy. The framework provided a complete, self-consistent description for systems in equilibrium, for states of static knowledge. The universe, however, is seldom static. The next great frontier lay in the turbulent, dynamic world of systems, driven away from this placid balance, a realm of irreversible processes, and the relentless arrow of time. The framework provided a complete, self-consistent description for systems in equilibrium, for states of static knowledge. The universe, however, is seldom static. The next great frontier lay in the turbulent, dynamic world of systems, driven away from this placid balance, a realm of irreversible processes, and the relentless arrow of time. To venture into this territory was to leave behind the certainties of equilibrium statistical mechanics. For a system undergoing that transformation over a finite duration, the venerable second law of thermodynamics offers a profound, yet incomplete, guide. It dictates that the average work performed on the system, which we may call the average of W, must be greater than or equal to the change in its equilibrium free energy, the quantity delta F. This is an inequality, a boundary. It sets a floor on the energetic cost of any process, a beautiful and unyielding constraint on the aggregate behavior of nature. Yet, it remains silent about the specifics. It describes the ensemble average, while revealing little about the individual microscopic journeys that constitute that average. What laws? Bennett began to wonder in the late 1930s. Govern the fluctuations around this mean? What precise, quantitative statements could one make about a system being actively manipulated, pulled, or pushed far from the placid state of thermal balance? This question marked a significant theoretical pivot. He was turning his attention from states to processes, from static distributions to dynamic trajectories. The challenge was immense. The elegant mathematics of the canonical ensemble, which he had helped to place on such a firm inferential footing, described systems at rest. A new physics was needed for systems in motion. His approach was characteristically audacious. He sought an exact equality where others saw only an inequality. He believed that hidden within the statistical noise of non-equilibrium processes was a deeper, more symmetric, and more powerful truth. His intellectual toolkit for this endeavor was assembled from the foundational work of his predecessors. He drew heavily upon Albert Einstein's 1905 formulation of Brownian motion, which had provided the essential mathematical language, the theory of stochastic processes, to describe the random, jetty path of a particle buffeted by its thermal environment. He was also deeply familiar with the recent work of Lars Onsager, whose reciprocal relations had established a set of elegant symmetries for transport phenomena in systems perturbed only slightly from equilibrium. Onsager's theory was a masterpiece of linear response. Bennett, however, aimed for something far more general, a law that would hold for processes of any speed and any magnitude, pushing a system arbitrarily far from its starting point. The result of this inquiry, sketched out in a series of letters and private research notes around in 1938, was a relation of stunning elegance and depth. It has since become recognized as the first articulation of the fluctuation theorem. Bennett derived an exact equality that connects the distribution of work values from non-equilibrium trajectories with a purely equilibrium thermodynamic quantity. The expression, which we might call a Bennett work entropy relation, states that the average of the exponential of the quantity negative beta times the difference between the work W and the free energy change delta F is precisely equal to 1. Spoken mathematically, the expectation value of e to the power of negative beta times the quantity W minus delta F equals 1. Here, beta is the familiar inverse temperature, 1 over Boltzmann's constant times temperature. Delta F is the free energy difference between the two equilibrium states that bookend the process. The crucial variable is W, the work performed during a single, specific, and unique realization of the transformation. The angle brackets signify an average over an infinite ensemble of these individual trajectories. This compact equality contains a universe of physical insight. It is a bridge connecting the messy, irreversible, path-dependent world of work with a pristine, reversible, state-dependent world of free energy. And it is an equality, holding true no matter how violently or inefficiently the work is performed. To make this abstract principle concrete, Bennett described a prescient thought experiment. Imagine a single colloidal particle, a microscopic bead suspended in a fluid at a constant temperature. This particle is initially in thermal equilibrium. Then, using a hypothetical apparatus akin to what we would now call an optical tweezer, we drag the particle to the fluid from one point to another over a fixed period. Each time we repeat this experiment, the amount of work required will be different. The random thermal kicks from the surrounding water molecules, the essence of Brownian motion, will sometimes conspire to help the particle along its path, requiring less work. At other times, these kicks will oppose the motion, demanding more work. The second law predicts that the average of all these work values will exceed the free energy change associated with the displacement. Bennett's relation predicted much more. It provided the full shape of the probability distribution of work values, P of W. His equality implies that observing a trajectory where the work done is less than the free energy change, a seeming violation of the second law's spirit is possible. Such events are rare, but their probability is finite and is rigorously quantified by his relation. The exponential weighting in the formula means that trajectories with large positive values of W minus delta F contribute little to the average, while the rare trajectories with negative values contribute exponentially more. These opposing contributions balance perfectly, always yielding an average of 1. This profound insight, however, fell into a silent void. The experimental means to manipulate single molecules and measure the minuscule work values involved were half a century away. The theoretical community was preoccupied with other matters, from the burgeoning field of nuclear physics to the formalization of quantum mechanics. Bennett's notes on non-equilibrium fluctuations remained an obscure, private rumination, a message in a bottle cast into the sea of scientific progress. Decades later, the bottle was found. In 1997, the physicist Chris Dzerzhinsky, working independently, derived an identical relationship. The Dzerzhinsky equality, as it became known, electrified the field of statistical mechanics. It provided a powerful new tool for computational and experimental physics. Almost simultaneously, Bennett's earlier work was rediscovered by historians of science combing through archival materials. In a remarkable demonstration of scholarly integrity, Dzerzhinsky himself, in his subsequent publications, took care to cite Bennett's rediscovered notes, acknowledging the extraordinary prescience of a thinker who had arrived at the same fundamental conclusion 60 years prior. This historical context was further enriched by Gavin Crookes, who in 1999 derived a related theorem connecting the work distributions for a process and its time-reverse counterpart, adding another layer to the theoretical edifice Bennett had first envisioned. Today, what was once Bennett's thought experiment is a routine procedure in advanced biophysics laboratories. Scientists use atomic force microscopes to stretch single strands of DNA or unfold individual protein molecules. By measuring the fluctuating work values for these irreversible processes and applying the Bennett-Dzerzhinsky equality, they can compute the equilibrium free energy of folding a central quantity in molecular biology. A theoretical curiosity from the 1930s has become an indispensable tool for probing the machinery of life at the nanoscale, a testament to an idea so fundamental that it could wait patiently for the world to catch up. This capacity for an idea to lie dormant, a seed of pure theory awaiting the technological soil in which to flourish, reveals the very essence of Bennett Williams' intellectual character. His career was a continuous, decades-long meditation on a single, powerful concept, entropy. Its meaning, however, underwent a profound metamorphosis in his mind, an evolution that mirrors the entire intellectual development of statistical physics itself. We see in his life's work the journey from a concrete, mechanical property to a universal principle of rational inference. Initially, in his early explorations of isolated systems, Bennett approached entropy through the lens of his great predecessor, Ludwig Boltzmann. Here, entropy was a geometric concept, a measure of volume in the abstract multidimensional space known as phase space, for a system with a fixed energy. Every possible microscopic configuration of its constituent particles, every combination of positions and momenta resided on a specific surface within this space. Entropy, in this formulation, was proportional to the natural logarithm of the area of the surface. It was a beautiful, almost tangible idea, a direct bridge from the deterministic laws of classical mechanics to the inexorable increase of disorder mandated by the second law of thermodynamics. This view provided a satisfying, self-contained explanation for how reversible microscopic laws could yield irreversible macroscopic behavior, a foundational paradox that had occupied physics for half a century. This elegant mechanical picture, while powerful, possessed inherent limitations. It described a world of perfect isolation, a theoretical ideal seldom encountered in reality. Bennett's own intellectual curiosity drove him toward the messier, more common scenario, a system in thermal dialogue with its surroundings, a cup of coffee cooling on a desk, a biological cell metabolizing nutrients. Here, the energy is a fluctuating quantity, rendering the fixed energy surface of the microcanonical ensemble inadequate. This challenge prompted a significant conceptual shift, guided by the towering framework of Josiah Willard Gibbs. Bennett's work on what we now call the Bennett distribution was his answer. Entropy ceased to be a property of a single state and became a statistical feature of an entire ensemble of possible states, each weighted by its probability. The system's interaction with a vast external heat bath meant that its precise energy was unknown. Entropy became a measure of the spread of possibilities, a quantity derived from the system's probabilistic dance with its environment. This was a move from the certainty of geometry to the language of probability, a profound abstraction that allowed physics to describe the behavior of open, interacting systems with stunning accuracy. Yet, even this sophisticated probabilistic view left a deeper question unanswered, a question that would occupy the final, most fruitful phase of Bennett's career. What, fundamentally, was this probability he was using? Was it an objective feature of the physical world, an intrinsic fuzziness in reality itself, or was it a reflection of the observer's incomplete knowledge, his encounter with the nascent field of information theory, particularly the work of Claude Jan, and later the powerful reformulations by Edwin T. Jaynes, provided the ultimate clarifying insight. Bennett came to see entropy in its most general and powerful form as a measure of missing information. This was the grand synthesis. The previous definitions were revealed as special cases of this universal principle. The Boltzmann entropy of an isolated system was the correct description when the only information one possessed was the system's precise total energy. The Gibbs entropy of a system in a heat bath was the correct description when one's knowledge was limited to the system's average energy. This principle of maximum ignorance became the supreme axiom. It dictated that the most honest probability distribution to assign to a system is the one that is consistent with what is known, while remaining maximally non-committal about what is unknown. It transformed statistical mechanics from a subfield of physics into a general method of inference for any system, physical or otherwise, where data is incomplete. This informational perspective allowed him to look back upon his own intellectual journey and see a single, unifying thread. Even his late career triumph, the fluctuation theorem relating work and free energy, could be reinterpreted through this lens. The irreversible generation of entropy during a process like stretching a molecule became synonymous with the erasure of information about the system's microscopic path. The theory was complete. Physics had become a sophisticated application of epistemology. To appreciate Bennett William is to appreciate the role of the conceptual synthesizer in science. His legacy is etched less in a long list of disparate discoveries and more in the profound act of reframing the very questions a field should ask. He gave us specific tools, like his eponymous distribution and his prescient non-equilibrium equality. His more enduring contribution, however, was a philosophical one. He taught a generation of physicists to view their discipline through a new prism, to see the towering edifice of statistical mechanics as the ultimate expression of rational inference applied to the physical world. His own intellectual path, from the clockwork mechanics of Boltzmann to the probabilistic ensembles of Gibbs to the informational paradigm of Shannon and Jaynes, perfectly recapitulates the grand arc of his science. We are left, then, with a compelling and deeply modern vision. In our current era, defined by computational science and machine learning, our most powerful intellectual tools are algorithms. They construct models of the world from vast, yet fundamentally incomplete, data sets. They learn to predict, classify, and generate by optimizing their parameters to be consistent with known data while making the most general assumptions about the unknown. In this light, are we all, in our collective scientific and technological endeavor, becoming practitioners of Bennett Williams' principle of maximum ignorance, or are we, perhaps unknowingly, extending his intellectual project far beyond the confines of theoretical physics, applying his core insight to unravel complexities he could have scarcely imagined, and in doing so, affirming the timeless power of his thought?
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.